that's one way we can classify devices. We can say this device is shared or dedicated or virtual. Other ways that we can classify devices, or storage devices in particular, like whether they are sequential or... So a device can be a sequential device where information of that device has to be read in sequence, as in the case of tapes, where you must read it from a particular point. You can't randomly jump to any point you want. If you need to get some information at that tape, then you have to keep reading it until you reach that point sequentially. Or if the device is a direct access storage device, DASD, known as a direct access storage device. A direct access storage device is a device which you can reach any point of it, wherever, if there's any file or any piece of data that's stored in any location in that file or in that device, then we can access it directly. So they are known as direct access storage devices. So all devices may be also classified as being sequential or direct access. And just talking briefly about those sequential or direct access, if you have a direct access device, you can reach any point you want directly. If you want to update a file, you can go straight to that file or that particular record and modify it. And therefore, this would be suitable for applications that require quick interaction with the user. So if you need a quick response time, if you want some information, you can go straight, get the information and present it to the user. So it has quite short response time if you are using the direct access device. If we are using a device such as a tape, for example, that you need to start reading, if you need that piece of data, you have to keep going through the entire tape until you reach that piece of information, that does not go well with applications that require, or that are interactive applications that require a short response time. Historically, the tapes have been around for a long time. They've been around since the 50s, and they were around before computers were in use. But as computers came, tapes were a very good form of storing information, even though they started with paper first, but they soon switched to magnetic tapes. So tapes are a wonderful way of storing information, but they had this problem of being sequential and being slow. And soon after that, in the 60s and 70s, the 70s, they started producing those disk drives that allowed direct access to every location, and they can store a pretty good amount of information as well. And you'd think by now the tapes would be out of action. They're so old, they're so slow, we can't use them for interactive applications, but they're still around. There are more tapes in use today in storing information than there are hard disks and other forms of storage devices. Any idea why? Any guess? Why are we still using tapes? Why are there so many tapes still in use around the world? Pardon? Yeah, well, okay, yeah. So it's the ability to store a lot of information, even though we can still store a good bit of information on hard disks, but tapes, they can store a lot more. And a lot more cheaper as well. If you consider the amount of data you can store on a hard disk or on a tape, tapes are way cheaper. And even though they are not suitable for interactive applications, but they are suitable for other applications, such as backup operations. So almost every organization, every big data user around the world, banks, organizations, insurance companies, hospitals, most likely at night they use tapes to store or do backup of their information. The other point is that they can carry a lot of information, huge amount of information. Right? You won't be able to access them, you know, on seconds or minutes, but at least if you need it, it's there and you can do a backup or recall it again if it's required. Probably 99% of it is never needed, or 99.9% is not required. But if you need it, at least you know it's there. So that's still in use, despite the fact that it's been so old and so slow and not suitable for interactive operation, but they're still in use in a big way because their ability to hold huge amount of information at a fraction of the cost of hard disks. So they're used for backup operations and other operations that does not require interaction with the user. Now, mind you, they're all known as magnetic storage devices. So you actually introduce a magnetic charge into a surface or an area that can be magnetized, so that the tape or the hard disk are impregnated with material that can be magnetized. And the way information is wrote onto it is by actually having a magnetic field that gets generated by the data based on the data that we are going to store, and that generates a magnetic field that aligns the surface of the tape or the hard disk as well, because the surface, the metal hard part of the hard disk, if we're looking vertically at a hard disk, or looking at it, say, from this point where the head as well is magnetically, generates a magnetic field to align some of the data that's there, or the magnetic material based, again, on the information that's passed. So it's basically what we do is we generate a magnetic charge and align those material there in a certain way that we can also pick it up. If we need to pick it up, it also will affect the reading head and will cause a magnetic field to be generated if we need to generate it. We should be able to regenerate it. So information is stored using this magnetic charge put onto the hard disk or the tape. But they have a slight disadvantage that with time, this magnetic charge kind of dissipates slowly and gets weaker and weaker. It takes like time of around 15 years or so. So even though they are long-term storage devices, but if you have a videotape that uses the same facility, and if it's any longer than 15 or 20 years, you start noticing that the quality starts going bad. And that's the problem with most magnetically charged storage devices. But looking at it, and we'll consider then the optical storage devices that are in the form of CDs and DVDs and other devices that use store information in the form of light or change in the surface. Looking at the surface, so if we're looking at the CD now, just horizontally, if we twist it around and look at it, the surface of the CD is actually, the information is stored in a different way. We use a laser beam on CDs anyway and DVDs. A laser beam is used that heats the surface. The surface has sensitive material that can get burned based on again on the information that we need to store, the binary from memory, that affects the light. And as the hard disk or the CD, rotates, we write on kind of tracks, spiral tracks here. I'll mention them now in a second. So you can actually, as you burn it, it kind of generates a little trough or a little bottom there and a top. And based on the ones and zeros, you can end up having the surface physically altered. And to read it, We use the less intense light that comes on, and as it's reflected, it's picked up here based on the surface, the reflection of the surface, and we can translate that into ones and zeros, and it should be the same material that was burnt. We'd be able to regenerate it by actually reading from, by reflection, the reflection of a lesser kind of intense light. And so basically there's no magnetic field involved here. There are other devices later on that were introduced. There were magneto that uses light or laser and magnet but we'll get to it in a sec. But basically, initially, the optical devices actually used light to burn or itch the surface of that device, and then by reading it is actually by shining a light again onto it and check the reflection of that light. Considering that, then there's no magnetic field involved in this particular one, and they claimed that any data put onto it, it will last forever. And because theoretically, yes, it should last forever, unless somebody breaks it or physically changes it. But in fact, they realized after a while that the actual metals that are made, that CDs, the surface is made of, they started causing corrosion after like 15 or 20 years. So they're working on improving those kind of material as well. So even though it doesn't dissipate like magnetic material, but the deterioration of the actual metal itself that could cause a problem. But whenever we store information on a hard disk, it's actually stored on what's known as tracks. So the tracks are just circles, concentrated circles, a full circle, one inside the other. And usually the hard disk rotates at relatively high speed. Anybody knows what the speed that hard disks rotate at?
7,000.
Oh, yeah. Okay, so pretty high speed, 7,200 RPM, revolution per minute. And as we move the head close, so whatever position we have the head in, it will cover one of the tracks. And the head that moves in, it's kind of they use what's known as a stepper motor that can go to one particular track. Ordinary motors, as they move and you stop them, they kind of tend to take slow a little bit and then stop somewhere. You're not very clear where they're going to stop, but with the stepper motor, you can actually stop it at certain points, very precise, and the technology improved that they can actually have them stopping at fairly close point, and each one of those points, as it stops there and disk rotate, that forms a track. And tracks are numbered, generally, from the outside track to the inside track. Usually, the most outside track is number 0, then the next one is 1, 2, 3, and the maximum, whatever the maximum is, could be 400, 600, or so on, on the inside tracks. So information can be written in any of those tracks. And whatever the total amount of information you can write on this track is the same amount of information you can write on the outside track. So it's on the inside track, it's a little bit more condensed together, while it's more spaced out on the outside track. Also, the tracks are divided into certain areas or certain lengths, and they're known as sectors or blocks, but refer to them as sectors now. So that's a sector there, from here to there. Many books draw it as this is the sector, and many students think this is the sector. That's not the sector. The sector is that or that or that from those areas. So the distance from this point to that point is a sector, or from that point to that point is a sector. Not the whole triangle there. That's not the sector. But that's a group of sectors. So that have the same number. And these sectors, each sector here is numbered. They're numbered from 0, 1, 2, 3, 4, and so on. And anything stored in a file now can be located by or identify the location for anything stored onto the device is determined by the track number. Let's say track number 76, sector number 3. So that means you go to track number 76, and the file is stored this here on this sector, for example. So you need at least those two pieces of information. And as you can see, the amount of information you stored on this sector is the same amount of information that can be stored onto this sector. It's just going to be a little bit spaced out on that sector. And just to get a little bit further on this one, with operating systems, they only deal an operating system whenever it's asked to read a record. Each time it comes to read a record, first it has to start the hard disk rotating, reaching that speed, and then it has the mechanism for the head. It moves the head to the correct track, let's say this track 76 here, and then if it needs to read that piece of information, obviously this is spinning so fast, so it might have just missed it now, so it has to wait until this track or this sector comes right underneath the head that it can pick it up. Pick that information up. So there are actually three kind of movements or mechanisms that are required. The rotation, moving the head to the correct track, and waiting for this correct sector to come underneath the head, and then actually picking the information up. And the total of this is known as access time for the hard disk, and usually every hard disk, it's stamped onto it how much is access time, and actually the hard disks are categorized by how quick their access time is, how short it is. So moving the head onto the correct track is known as seek time. So that's the seek time is the time it takes to move the head, that slight movement, to move it onto the correct head. It takes a few thousandths of a second or a few hundredths of a second, but it's part of actually the time delay that forms the access time. And then after that, once the head is on the correct track, then it has to wait for based on the speed here, we'll wait for the correct sector to come under the head, and that's known as rotational speed. And then finally, once the correct sector is under the head, then the information is picked up through the electromagnetic field that affects the head, that can translate that into an electric signal, and that's called what is it known as? Transfer speed time, or transfer time. So access time is actually made up of those three times together. And some hard disks, they actually don't have a seek time. They don't have the head moving. Any hard disk that has a moving head, it's just known as well with that. It can be classified as, is this hard disk, is a moving head disk, or is it a fixed head? And if it's a fixed head, some devices, they actually, all the sectors that they have, all the tracks that they have, they actually have hard disks or heads, so many heads, one is lined up with each track, and they're all there forever. They're staying there, they're fixed, they don't move. So anytime you want to read data from that, there's no seek time involved. And if this rotates at 7,200 or higher, then you're going to pick it up, it's going to be very short time, and transfer is even shorter. So some hard disks, they have what's known as the fixed head, and that fixed head makes those hard disks, it makes them very high, very fast, very short access time, but also very, very expensive. That's not the kind of head you'd find in your laptop or your desktop at home. These are reserved for very expensive, machineries or devices or systems that require a very fast access. Things like spaceships or airplanes or real special devices, maybe military devices. So at the moment, most of what we have, you and I have, are the ones that have one head, not multiple heads. One head, and we move it on top of the required track. And that involves that extra delay of seek time. Now, looking at the, okay, there's something called buffering or blocking. I'll talk about it in a second, but just I'm going to look at the optical disc just while we're looking at the hard disk. The format of the optical disc is the way information is stored onto the optical discs. Optical discs don't have concentric circles. Information is not stored on concentric circles. They actually on one single continuous track, spirally kind of track that you write the information on. And the information on it, whether you're in the inside or the outside, it's well compressed. Remember here on the outside track, it's well spaced out on a hard disk, while on a CD, it's compressed here as well, the same as on the inside track. That's why we can store a lot more information. With hard disks, there seems to be a lot of wasted space, especially on the outside tracks. Well, while the inside tracks are well packed, but the outside tracks are not. On CDs and DVDs and other devices, they're all packed quite well at all different parts of the device. And therefore, we can store a lot more information on those. And therefore, those sectors or blocks, they're also equal. They carry the same amount of information. But the same amount of information on the outside track might be there. That takes that distance, takes the same distance on an inside track. So an inside track it might take this much distance, so that's all one track. And therefore, they're not all lined up. They'd be out of line because the inside circles are smaller than the outside circles, and therefore they don't seem to be lined up, but yet they are equal distance. They have equal distances in length. While on hard disk, they don't have equal distance in length. They have rotational distance, that's to say. They have the same angles, but not the same distance. Here they have equal distances. And therefore, as the information is being read, it has to pass under the head at the same speed, and therefore, going here, rotational speed has to be equal. Like the length that goes under the head here in 1 second or 1/1000th of a second has to be the same as this one here. And therefore, the actual speed of the disk tends to change for when you're on the outside track, reading from the outside or reading from the inside. So it tends to be faster as you're on the outside than, or it's the other way around. So it slows down here, so it will cover the same distance, but to the outside distance, right? But overall, it should be the distance underneath the head should be the same at the same length of time. Right. Now, whether you're reading from a hard disk or from a CD or a tape or whatever, usually it will involve a delay, enormous amount of delay compared to the speed of memory, main memory that uses electronics moving around, which is very close to the speed of light, or compared to the performance of the CPU. Hard disks are still very, very primitive devices or very slow devices. And in order to improve that, the operating system uses buffering, just similar idea to spooling that we used for printers. So in main memory, for example, any time you say read a character, let's say open a file and read one character, the operating system never reads one character. What it does, it reads a complete block or the information stored in a sector. So it brings all that, because I might as well, by the time you get this rotating and you move the head across, and the head just go over that, underneath that space goes under the head in a fraction of a second, it picks all that information, puts it there in main memory. And then it gives you that character that you want. And if you ask for a second character, then it doesn't have to go to the slow hard disk. It already has it in main memory. It gives you the next character next. And if you don't ask for it, if your application does not ask for the next character, Okay, well, just, it'll ignore it and it'll discard it. But while it's going to the hard disk, might as well, instead of going to read one character, go read the whole lot. So it's like if you're maybe going to town or going somewhere for a shopping, you might as well get the week's supply rather than you go for a bottle of milk and then a piece of bread. You go again for a packet of cigarettes or whatever. So this is the kind of thing. Whenever the operating system gets asked to read a character from a hard disk, it never reads a character and it never writes a character. It just reads a block. And if you say, write this character to the hard disk, it will take it into memory and write it. If you say, write another character to the file, keep writing to the file until it has big chunk, one block of data, and then it will write it and go once and write it there. So instead of going 500 times to the hard disk or 5,000 times, it only goes once. And that improves speed tremendously. And this is known as buffering. So once you open a file and you say read from it, one character, one byte, one record, it reads as much as it can. Usually it reads one complete block and passes you the whatever you need. That's known as buffering. So some amount of main memory, a buffer in main memory, is allocated for this particular purpose, to improve the performance of hard disk or reduce the effect of the slow hard disks compared to the CPU. Now, another point to worry about or to consider, see, whenever you're asked to format a hard disk, for example, it's up to you. You can change the number of tracks up to a certain maximum, but most likely what's more important is the sectors. It'll ask you how many sectors do you want. And it's up to you. You can have as many sectors as this one, or you can have less sectors. So once the hard disk is formatted, you can say, all right, I just want few sectors. So basically, you can have big blocks or smaller blocks. And the difference between them, I don't know, which one is better? Is it better to format our disks into larger blocks? Or the same hard disk is not going to change the amount of data, the total amount of data storage that you can store. For example, if this is the hard disk, same number of tracks, and you can store, the amount of data is how much you can put on each track. That doesn't change. You still place in the same amount. But are you going to have, for this particular disk, you're going to have, for example, 8, maybe sectors, or maybe 16 or 24 or larger number of sectors. Which one is better? Anybody has any idea? Okay. Yeah. Any other opinions? That's correct. If you want each time you read, you want to read a big chunk of data, then this is the better the blocks, the better the less. That means the less times you need to go to the hard disk. Any other reason for going for smaller? What's the disadvantage then of having the bigger blocks? Why don't everybody forget about, small blocks here, so I'll go for large blocks. It takes the same amount. On the hard disk, it doesn't make any difference because you're storing the same amount of data. Well, yeah, let's say you might need some extra memory, but once we provide the memory, then if that's the only thing, then we provide extra memory, and we always have. Everybody has bigger blocks. What's the disadvantage of bigger blocks?
The information you want is divided into different blocks, all right?
Yeah, well, it'll be one block here, one big file. For example, here, let's say even maybe 2 blocks. Let's say we have a file this big, takes 1.5 blocks. This one here, it's the same file, same size. It will go as far as here, so it'll take 1, 2, 3, 4.5 blocks, or even more. Maybe say 10.5 blocks. So what's the difference?
Maybe I just need the piece of information I need. It's in the smaller part of it, in the smaller want to go for a big block to get this information, whereas you can just go for just a small block?
Well, see, the operating, you will, I don't know what way, for example, we need to access the file, but when you ask the operating system for your file or bring you the file, it's up to you then as an application. How am I going to access that file? Am I going to go for it sequentially, or do I have a random access? If you have random, you'll be able to go straight for the record if the record you're looking for is here. Well, that's internally how are we going to access that file. Okay, anybody else? Anybody has any other opinion as to what are the benefits or disadvantages of large or small blocks? Right, okay.
There would be slightly more overhead if it's smaller blocks, because you have to keep reading, there's more information.
Yeah, absolutely. If we have large files like this one here, or even larger, then in order, for example, it appears even easier if I say copy this file. How long will it take? How many times do you have to go to the hard disk? Remember, each time you want to read a character or a file, the operating system will read you one block at a time. So in this case here, for example, if you need to copy this file, you need to read that block there and write it to, for example, you're going to write it here. So whatever. So that block is written here. And then we come back, read the next block and write it there, and there it is. And the file is finished. We finished copying the file into 2 visits to the hard disk, or 4 in this case. But we read this file into 2 visits. And that's what's slow about the operation, is how many times do you come to the hard disk and move the head and locate the item you want to read and read. But once you come here, the operating system will give you 1 block. No more, no less. It will always tend to do that. So in this case here, it will take us 2 visits to read the file and maybe 2 visits to write it. While here, if you need to copy the same file, then you have to come back 1, twice, 3, 4, 5 times, and then to write it then another 5 times. So the bigger the file, the better it is to read it or write it if you had bigger blocks. That means less visits to the hard disk. If you have a very large file and very small blocks, then you might have to do that operation many times. But look at the other way around. Let's say you want to create a file. You ask the operating system, you have a file, you start writing your report, and you wrote 1 line or 1 word, and you say, save this file. How is it going to save it? The operating system, again, will not allocate you 1 byte or 10 bytes of a file, it will also allocate you a block. So in this case here, it will give you this block, and you've only written 1 word into that file. So most of the space in there is wasted. And if most of your files are very small files, then most of your hard disk is going to be very badly used. Because every block, every storage space we give you only use 10% of it. That's 90% of waste. While if we had smaller blocks or sectors, then each time we give you a space, it's not going to be very big anyway. So even if you use a small bit of it, that's going to be minimum amount is wasted. So the smaller the blocks, the better and more efficient use of storage devices. But it will take longer to read or write from, especially larger files. If we have a bigger blocks, it will mean less visits to read a file to the hard disk, so it's going to be faster reads and writes, but it could mean bad utilization of storage space. So if you join a company and they happen to be formatting their machines and you are asked, we're going to format, how big is the sector? How big, what size sector should we have? How would you determine what's the best size? Say again?
What type of
Yeah? So get the profile of the filing system in how big are the files? What's the average size of files in that organization? If it's a video editing creation company, then they're going to have very large files. That's what videos, normally. Then you go for bigger blocks, because it means they'll have faster operations of copy and writing. And even if they do create a file, they put a video is big anyway. Even if it doesn't fill a block, it's going to fill most of it. So there'll be less storage space. But if the organization mostly has lots of small files, large number but of very small files, don't go for the big blocks, because if you give a small file, you give it very little, a big complete block is given to a small file, you'll have a lot of wasted space, so it's better to go for much smaller block sizes. It'll have less wasted operation, and we're not going to be wasting too much reading, because the file is not going to be much bigger than 1 or 2 blocks, or maybe 3 blocks at the most, because most of the files are small. And if only the odd file is large, that's okay as well. So that's with hard disks. So which one is better? Just a quick question. The hard disk or a tape? What do you think? A tape? It depends. Yeah, very good. Give me one reason why you say, hey, tapes are better in this case. When would you go for a tape? If you have a backup, if your applications do not have interactiveness with the user, then yeah, if you don't need a quick response, yeah, go for tapes. Why would you go for tapes? Because they are cheaper and they can store a lot more data. So far anyway. And you'd go for hard disks if you have interactive operations. Like people go into a bank to lodge money and do their transactions. They want immediate action. They want quick response. You can't have a tape. In the old days, 50 years ago, 40 years ago, we used to have tapes. And you don't do your transactions directly. You do it and they keep a record of it and they store it, and then at the end of the day they do a batch operation. They go through all the transactions of the day. They update the main files. But now files are updated immediately. Every transaction you do goes to your main file. That can only be done if we have direct access to those files. So hard disks are obviously very important. And they are important because of the response time, because of the interactiveness that they provide. They're still relatively slow and primitive compared to the CPU, but that's the best we have at the moment. So, so we try, and the operating system tries to improve the performance of hard disks. So, and that's what we look at now, the strategies of improving performance of multiple requests that come into a hard disk. So what's the best way to improve it? So let's have an example first, and we'll work on it. So remember, on a hard disk, as I said earlier on, the tracks are numbered from 0, 1, 2, 3, all the way to whatever, track number 800 or 1,000 or whatever the maximum number. That depends on the hard disk and on the quality and cost and storage capacity and all that. But we have a minimum starting 0 on the outside and working in towards the center. And remember that each item stored on a hard disk is determined, its location is determined by the track that it falls on and the sector it's on. Also, there's another aspect of hard disks. Now, again, if we rotate this hard disk and look at it cross-sectionally, you'll see a hard disk something like that. And the surface of the hard disk is the part that's impregnated with the magnetized material, or material that can be magnetized. And that's the one that we can write onto. And usually the head, you could see the head is something like this on top of the hard disk, that we can move it in or out, or to just, say if you're looking at the head here, that could be the head that can move onto the correct track until, so that's what it might look like. And in most hard disks, you can actually write on both sides of that disk. So you can actually have tracks on the top surface or on the bottom surface of that disk. And on most of them, so even though, for example, it rotates around that, it's actually they have a second, or maybe sometimes more than a second, a few disks that are fitted onto the same component, and they call this a disk pack. So you can have a pack of disks on the same hard disk, in the same housing. And in fact, you'll have the head that goes in there. You have two heads, one reading there on that surface, and one reading from the surface of the next disk. And also on both sides, so you can actually do the same thing here. And if there's even another one, and they all rotate together. And the heads here, sometimes they don't use the bottom, the outside, the very top surface and the very bottom surface. In some hard disks, they don't use them for storage, but on others they do. So they're all connected together, or they should be connected together. And they all have the same mechanism. But once you push them in, all the heads go on together. Pull them out, and they all move out together, all the heads. So if this head is on track number 10, so is this one on this surface. It's on track number 10, and so is this one. And once they're all the heads are on the same track, whatever track it is. And that track, they call it a cylinder. So a cylinder is on one of those packs, on a hard disk pack where there's more than one disk or one surface for storage. A cylinder is all the tracks that share the same number. Wherever that head is on at that moment of time, then all the tracks. And what's so special about a cylinder? Right, so what? Track number 7 here, same as we are reading from track 777. Imagine if we have a big hard disk on one surface. No, a big file, sorry, on the same surface. Let's say most of the time, allocation of space is random. You don't always get the same space continuous on the same hard disk for a file. Sometimes you do, but sometimes you don't, not necessarily. So if you have a very large file like this, it could be on the same track. But more likely than not, you're going to have, you ask for a space, you're going to open a new file, you're given this block, and you start writing. This block fills up. You say, I need to write another, more space. They give you another block. It could be here. The operating system will link that to that. It knows that belongs to the same file. And then you need another block, and it could be here somewhere. And another block. So the same file could be made up of so many different blocks in different areas of the hard disk. So if you're reading this file, you'll have to move the head in, read that block, copy it, and then you want to read the other block, so you have to move. There's block number 1, block number 2, so you have to move it out to this track. So you keep moving the head. That movement of the head is known as seek time. You're actually doing a lot of seek time wasting. Imagine if you had a cylinder, and if you had this block here on cylinder, say, 22, also, this block, instead of putting it there, let's put it onto this surface here on the same cylinder, 22. So you can fill this cylinder and then go to the same cylinder. So the same file can be read, doesn't matter how big it is, by just placing the head in one location, and you can read it on different pallets or surfaces of the same hard disk without actually any further movement of the disks or of the heads. And that kind of tends to improve performance. So, in a way, it's important. The cylinder is an important part. Even though it's conceptual, there's no such thing as a cylinder. But all the tracks that form the same number, they're known as the cylinder with that number. So even sometimes some books define it. They say, what's track 50? What's cylinder 50? It says all the tracks on the disk pack that have number 50, they form cylinder number 50. Have we signed the attendance sheet? No? Yes? No? What time do we finish? Oh, right now then. Okay, so maybe we should speed things up. Any questions, guys? No questions. Great. I'll ask a couple of questions. What's a cylinder?
It's the same track on different surfaces.
On different surfaces, yeah. And what's a track? What are tracks? Yeah, concentric circles. Are they just one continuous circle, or? Yeah, one circle inside the other. And what are they used for? Yeah, that's where information is stored, along those tracks. And what's a block or a sector? Anybody?
A group of tracks.
Sorry?
A group of tracks.
A group of tracks? No, a part of a track. Okay, sorry, one at a time.
On a tape, it's a group of records.
Say again?
On a tape, a block is a group of records.
No, I'm talking about, oh, yeah, no. Let's stick to hard disks.
It's a part of a track.
Yeah, a track is divided into equal sized sectors, sometimes known as blocks. Okay, and it's also normally the unit that the operating system uses to read or write from or to a hard disk. What's the DASD? What does it stand for? Direct Access Storage Device. And which one is better? A hard disk or a CD or an optical disk?
Depends on what type of files you're using it for, like whether it's backup files or
Which one is faster at reading and writing? An optical disk or a hard disk?
An optical disk, because it's not dependent on the heads.
Hey, any answers? Any other answer? Hard disk is faster?
Fixed head.
It has what?
Fixed head.
Oh, the fixed head. Yeah, definitely. The fixed head is faster than the moving head or movable heads. But just considering movable heads on hard disks or CDs and DVDs or optical disk drives, hard disks tend to be faster up to this stage. You can store more information on the same size CD or DVD on track, per track.